In the previous video, we saw how we can understand and define a directed path and how we can take a vector field and resolve it along the tangential and normal components of that directed path. In this video, we're going to establish a relation between the flux and the divergence, and along the way, also the relation between curl and what is called the circulation. And in order to do that, let's consider again a two-dimensional flow field. But instead of considering an open path, just to be clear, what do I mean by an open path? So in the previous video, and I'll put a link to that previous video, we considered a path, let's say from point A to point B, and we made an arrow in this form, which means that as I go from point A to point B, I am traversing this path along the directions pointed by this arrow. And at each point along this path, the arrow essentially points along the direction of the tangent to that curve. And I can define what is called the normal to the curve. And our convention is that if you imagine yourself walking along this path in this direction, then your right hand will point along the direction of the normal. Now, the way we have drawn this path from point A to point B, it's an open path because the path doesn't close in on itself. So for instance, if I had a path which went like this, and then it closed in on itself in this manner, this will be an example of what is called a closed path. So let's consider a very simple example of a closed path. Again, we'll restrict ourselves to two-dimensional flow patterns for now. And in the process, let's see how we can define the net flow across that closed path, as well as what part of the flow is not crossing that path. So what part of the vector field is moving along that path. And this will give us a way of finding a relation between the divergence, which we have defined before, and what is called the flux, which is the flow across a path, as well as a relation between the curl, which we have defined before, and what is called the circulation. So let's see how we do that. For simplicity, I'm just going to consider a rectangular path and imagine that this is an infinitesimal rectangular loop. So it's a path in the sense of a closed path. So it's a closed path which is closing in on itself. Let's say we define the direction in which we traverse this path in an anti-clockwise manner. And imagine that this loop is placed centered at the point x comma y. We're going to impose some dimensions to it. Let's say the dimension along the x-axis is del x, and the dimension along the y-axis is del y. And eventually, we'll take the limit that del x tends to 0 and del y tends to 0. By the way, this is very similar to the kind of derivation we did when we defined how sort of we can relate the changes in pressure in a fluid, how the gradient of that pressure points in the direction of the force field. So I'll point you to a link where we discuss this idea in detail. And in that video, we considered this kind of an infinitesimal cuboid. We took the pressure gradient, the changes in pressure across the faces of that cuboid. So this is a simpler version of this, except that pressure is a scalar. And in this case, we are considering a vector field crossing an infinitesimal closed path, right? All right, so let's say we have this closed path, and I'm going to maybe draw some representative vector fields. So maybe now just for clarity, what we're going to do is we're going to take the center points of all of these sort of sides of the rectangular path, and I'm going to draw a vector field at each of these center points. And I'm just going to explain in a moment what it represents. So let's say this is the velocity vector field located at this particular point. Now, this point, if this is the center point of the rectangular loop, then this vector field I can resolve into two components. And just to be clear, let's also make some coordinate axis. So we have this XY coordinate axis, and this will make it easier. The choice of the rectangular path will just make it easier for us to define the tangent and the normal directions to the path, right? So if this is the coordinate axis and we have this rectangular path in the way we've just drawn here, we know that as I move from, let's say, this point to this point along this arrow, the tangent is along the y direction. And if I use the convention that the normal will always point along the right hand of any person, let's say you, who's walking along this path from this point, from point A to point B. The normal will point along the direction of your right hand. So that's normal. And so the normal for us would just be along the x-axis, and the tangent will be along the y-axis. Now, as you go from here and maybe reach this particular segment, the tangent now points along the negative x direction because you're moving along the path. And the normal will again be along the right hand, along your right hand. So the normal will point along the positive y direction. As I reach this particular segment, the tangent will be along the negative y direction. The normal, again, our right hand would now be pointing in this direction. So the normal will be along the negative x direction. And as I move along this particular segment, the tangent will be along the positive x-axis and the normal will be along the negative y direction. So that's kind of the convention that we'll be working with. So now imagine that we have a vector field, and I'm going to resolve it into two components, one along the normal and one along the tangent. And let's say one along the normal, we'll just call it as P. And for us, that's the x direction, plus the one along the tangent, we'll just call it Q. That's pointing in the y direction. Now, some of you might be using I hat and j hat. That's perfectly fine. And some of you might want to use the normal vector and the tangential vector. That's fine too. So you can use any convention, any notation you want. All right. Now, let's make some representative. Let me just draw this rectangular path again. So hopefully the tangent and the normal directions along the segments of this path are clear. So let's make some vector fields now. So we have a vector field. Maybe I'll use the white. So we have these vector field, and let's say the vector field is a velocity vector field. So the vector field would be defined at every point in space, right? So it'll be, say, V, the vector field is V, and let's say we have two of its components. And for shorthand, I can also represent the two components as P, Q. You can use any notation you want. But this vector field would be a field which will be defined at every point x, y, which means if I were to really draw the vector field, then the vector field along this particular segment, for instance, might look something like this. So you'll have to draw a lot of these arrows. But what we're going to do is we're going to say that, okay, this segment, which has a length of del y, is so tiny that we're just going to make one representative arrow at the center point of the segment, with the assumption that the vector field is fairly smooth, that it doesn't change much along this particular segment. So if I were to pick this one as my representative arrow for the vector field, now notice the way I've drawn it, all the arrows are pointing roughly in the same direction. There might be slight, very, very tiny change in their lengths, very, very tiny change in the direction, but we're just going to ignore that for the moment along one particular segment. So along one particular segment, we're going to say that the segment is so tiny that the vector field is approximately constant and it doesn't change much along this segment. Now, as you go from this segment to this segment, we need to capture perhaps a slight change in that vector field. So maybe when it reaches here, the vector field might look like this. So its direction has slightly changed. Maybe its magnitude has slightly changed. So we're going to draw that representative vector field at the midpoint of this segment. And we're going to say that, okay, along this segment, the vector fields are approximately represented by the one that we're drawing at the midpoint, because again, the length of the segment is very, very small. Similarly, as you go from here to here, the vector fields might look like this, right? So the underlying assumption is that the vector field is smoothly varying across space. It's not undergoing very, very rapid or very, very sharp transitions. And if you were to express this more mathematically, we're just going to say that it varies continuously, very smoothly along the space that you're considering, right? Which allows us to make one representative arrow along each of the tiny segments. Remember the word tiny. If it's a big segment, it's a finite line segment, you'll have to make several such arrows. But for a tiny segment, we're going to make one representative arrow for that vector field. And hopefully this idea is clear. So coming back, I'll make another representation of this particular rectangular segment. So the segment is located on the point x, y. I'm going to take the midpoint of this segment. I'm going to make one representative arrow of the vector field. I'm going to take the midpoint of the upper segment. Maybe we can even label the segment. Let's say this is segment 1. This is segment 2. And perhaps maybe we can use different colors just so that it's clear. So we go to segment 2 like this, and I'll make a representative arrow, that's segment 2. Then we're going to reach segment 3, which will be this one. I'm going to make a representative arrow like this, and we're going to reach segment 4 like this, and I'm going to make a representative arrow in this manner. So these are the 4 segments and the 4 vector fields, right? Now, let's come to the crux of the matter. So we have the vector field, velocity vector field like this, and I have 2 of its components, pi plus qj. P is along the normal and q is along the tangent. So if I want to write the vector field at this particular point, right? This particular point is located, now remember that the dimension is del x and del y. So this particular point is at x plus del x by 2, comma y. Because this is the midpoint, you take a del x by 2 step away to reach this segment. So the vector field here has a magnitude and direction located at the point x comma del x by 2 comma y. So I have 2 of its components. So I can write the vector field there along segment 1 as p x comma del x by 2 comma y, that's along the I direction, plus q x comma del x by 2 comma y along the j direction, right? Likewise, you can draw the vector field. Maybe we'll just write it down for all 4 segments. So the vector field at segment 2, at the midpoint of segment 2, will be at p. Now this point is del y by 2 up from x comma y, but the x coordinate doesn't change. So this is x comma y plus del y by 2 along I plus q x comma y plus del y by 2 comma j along j. Similarly, we can write the vector field at the location along the segment 3. Now here, x is shifted backwards by minus del x by 2, or rather by del x by 2. So this is x minus del x by 2, whereas y remains what it is. So it's I plus q x minus del x by 2, comma y j. And along segment 4, which is this one, the velocity field is v4, which is p. X doesn't change, y is y minus ly by 2, I plus q x comma y minus del y by 2 j. Now, recall the discussion we had in the previous video. Let's find out how much of this velocity field is crossing this path. Now, what do we mean by that geometrically, at least in the kind of diagram we have made here? Now, notice that the vector field here along segment 1 is pointing away from the path, right? It's pointing in this direction. So which means that if I were to consider this as one open segment, like the one we had in the previous video, the normal component of this vector field, which will carry the fluid away from this region. So if this is the internal region, the normal component of the vector field along segment 1 will carry fluid outside from the region. Conversely, if I look at segment 3 here, the green arrow is coming inwards, right? It looks like it's coming inwards, which means that if I were to take the normal component of the green arrow, it's bringing the fluid, bringing the vector field inside of this region. So the net flow, perhaps we can want to calculate the net flow outside of this region. Then the net flow outside of the region will be the one that's flowing out from here minus the one that's flowing out from here. However, this is just the components which are taking the flow away or into along the x direction. There is also the component of flow which is coming in or going out from along the y direction. So for instance, here, if I were to look at this vector field and were to take the normal component of this vector field like this will carry some flow away or along the positive y direction. Whereas the blue arrow here is bringing in flow again into this region, but along the y direction, right? But overall, if you were to just be interested in the total flow outside of this region, then at least in the way we have made the diagrams, this segment is perhaps carrying flow outside. This segment is carrying flow outside, and these two segments are bringing flow inside of this region. So I can try to write down what is the net flow outside of this region. And that is the reason why we were considering a closed path. So this is a closed path. There is some flow. Maybe I'll draw it again. Maybe this is some closed path. There is some flow coming in from different direction like this. And there is some flow going out. And we are interested in finding out what is the net flow, net velocity flow, or any kind of vector field you're interested in, net vector field flowing outside of this region, right? So we're just going to take the normal components along each of the segments, and we're going to sum it up. In some directions, that normal component will be negative. Along some segments, it will be negative. And in some directions, it will be positive. And we're just going to sum it up. Okay. So let's look at segments. Let's begin with segment 1, right? So I'm going to write the net flow. And remember that this is an infinitesimal segment. So we're going to write maybe this notation, net flow del F. That's some flow. Okay. So the net flow from away from this region would be segment 1 is carrying flow along the x direction, right? So the normal is along the x direction. So this is segment 1. This is the x direction. So we pick out this component. The normal is along the I direction. If I were to dot the vector field with the unit vector along the I direction, I'd just be left with x plus del x by 2 comma y. So that's one component, x plus del x by 2 comma y, right? Now, along this segment, we made one representative arrow at the midpoint of the segment. This arrow was representative of the vector field which exists all along this arrow. So the total flow across the segment is not just given by the vector field which exists at the midpoint, but it's this nearly constant field along this segment times the length of this entire segment, right? So if I were to make one arrow and we were to make the assumption that this arrow roughly remains constant along this segment, then the total fluid which will flow outside of this segment will be whatever is the velocity, the magnitude of velocity along the x direction. This is for segment 1 times the length of that segment. So the total flow outside of this segment 1, would be the x component, which is normal to that segment, times the length of the segment, which is del y, right? This is how we define the total fluid flow, total fluid or total vector field flowing across a segment of some particular length. That could be an infinitesimal length or finite length, but for a finite line, the vector fields will keep changing direction. For an infinitesimal vector field, for an infinitesimal segment, we can make the assumption that the vector field is nearly constant along that segment, and we just multiply it by the length of the segment. So that's the net flow away from the region along segment 1. Similarly, the net flow from segment 2 here would be the y component of the vector field defined there times the length of the vector field, right? So if I were to make the diagram again, just for convenience, the net flow here would be this component times this length. Here would be this component, which is pointing in this direction, times this length. Similarly, here would be this component times the length, and along here would be this component times the length. Okay, so for segment 2, it'll be Q. That's the component which will carry the flow across the segment Q, but Q is defined at x comma y del y by 2, and the length of the segment there is del x, right? Now, what about segment 3? And remember that for segment 3, the vector is pointing in this direction, right? Since it's smoothly varying, since the vector field is smoothly varying, we've made the vector field in the manner that it goes like this, 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 and this. So it's still pointing roughly in the direction where the vector field along segment 1 and 2 are pointing, which means for segment 3, it looked like it's coming inside this region, right? Because the normal is defined away from the region in this manner. So what will happen is that if I take the vector, the velocity field along segment 3 and dotted with the normal for segment 3 would be along minus I direction, right? It's towards our right as we traverse the segment along the tangent along the direction which is pointed by the arrow, which is B, along the tangent to the segment. So the normal would be along minus I. If I dot it with the vector field, I'll pick up a negative sign here, and this will give me P x minus del x by 2, comma y. The length of the segment is still del y. Likewise, for segment 4, there is flow coming in because the normal to the segment, and if you want, I can just draw this diagram again. So the normal here is here, 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 whereas the vector field here is like this. The vector field here is like this. So if I dot this vector field with the normal, the net result would be something which will pick up a negative sign, right? So we'll have minus q defined at x comma y minus del y by 2, and the length of the segment is del x. Now, that's the net flow outside, away from this region, right? Because we have, by assumption, we have taken this to be positive, right? So if I combine these terms, and again, this kind of algebraic manipulation would now be familiar to you because we've done that a few times already. So if I look at these two terms, it's only the x component that's changing, whereas y is fixed. And that's how we define the partial derivative of some function with respect to one of the variables, one of the independent variables along which it's changing, right? So these two combined together, and you can use the Taylor series expansion as well, which is again something we've talked about before. So maybe I'm going to use the Taylor series just to make this thing clear. So if I look at this term and I expand around x comma y, so the first term I'll pick up would be minus dou p dou x. So that's p x comma y times del y. Then if I expand this to first order Taylor series, I'll have minus dou p dou x times del x by 2. And there is this del y, which is a common factor coming in both the terms. So I'll pick up this. I'm going to expand this term now, and this will give me minus p x comma y, again del y. But notice that there is a negative sign here, and there's a negative sign here. Together they cancel out, and they'll give me a term which will be dou p dou x del x by 2 del y. So that's coming from this and this. Likewise, I can do a Taylor series expansion, but this time along centered around x comma y, but this time expanding in the variable y, which is because for the q terms, it's only y which is changing. So I'll pick up a term which is q x comma y del x plus dou q dou y del y by 2 del x. That's coming from here. And then we'll have minus q x comma y del x plus dou q dou y del y by 2 del x. Del y by 2 del x. Sorry about that. Now notice that this term cancels this one. This term cancels this one. By the way, I made an error. This will be a plus here. So this will be a plus sign here. All right. So these two terms, however, add up, and these two terms add up. So overall, the net flow is tau p tau x. Now notice there is a factor of 2, factor of 2. I can combine them. We have del x, del y, plus I combine these two, dou q, dou y, del x, del y. Now this left-hand side is what the net flow across this region is what we call the flux, or in this case, the infinitesimal flux across the region. So this is called the infinitesimal flux. And flux literally means flow. Now, del x, del y, if you remember, was define the dimensions of the infinitesimal region that we considered. So del x times del y is the area of the region of the infinitesimal loop which we considered. And this is common between these two terms. So I can take this on the other side. Maybe I can write this as del A. So let's define the infinitesimal area as del x times del y. On the right-hand side, I have dou p dou x plus dou q dou y. And this is something you recognize by now. This is nothing but the gradient of the velocity vector, the divergence of the velocity vector field. That's del dot v. So this is the divergence That's the del operator dotted with the velocity vector field. And this gives me the divergence of the vector field. So, and notice this interesting relation that we have just discovered for ourselves, which is the divergence of the vector field across this region captures the net flow, the flux across this region, normalized by the area, in this particular case, the area of the region. So if you think of this as a flux density, that's the net flow divided by the area, then the divergence is equal to the flux density across that region. So this is divergence, and this I can write down as the flux density. Right? So hopefully this idea is clear. If you look, there's some interesting things you can now do. For instance, as two quick exercises. One, instead of considering the normal component of the vector field along each of the directed tiny segments of the closed loop, what if you consider the tangential components? What do you think we'll get? That's one exercise. The second one is, let's see what dimensions do we get, physical dimensions of the divergence do we get if we were to do some kind of dimensional analysis. Let's say this is indeed a velocity field, and this del we know is defined as dou dou x I plus dou dou y j. So it's 1 over some length. So what do you think are the dimensions of the flux density or the divergence, at least when v is a velocity field? So I hope you found this informative. Do comment, do write what your solutions to both these quick exercises are, and I'll be happy to take this discussion forward with you. Do like, do subscribe in case you find this content useful, and support us in bringing more such content for you. Happy learnings. Thanks for watching.